I'm Simon Turner, and I've been, as Joe said, working on interrupted time series since my doctoral work. Today, we're just going to sort of give an outline overview of how to analyze an interrupted time series. And we're going to work through some descriptions of interrupted time series studies, how to measure the impact of an interruption, and then we'll go through an example of an actual statistical model, how we might then obtain effect measures of interest. We'll talk about some of the complexities of time series data and why, as a systematic reviewer, this is all important to know in case we need to reanalyze data. So not all public health interventions can be evaluated with a randomized controlled trial. Interrupted time series studies are particularly useful in situations where it's impossible or unethical to separate groups. Here's an example of a country-wide interrupted time series study looking at the effect of bicycle helmet laws for children. Obviously, we can't separate the children to not wear helmets on one half of the country and wear helmets on the other half of the country. That's wide scale. We can also do very small interrupted time series. Here's an example of a hospital-wide antibiotic stewardship program. So we can use interrupted time series studies to address issues where perhaps we've got lawmaking or doctors working in a hospital. They're also quite useful to estimate the impact of natural disasters. At the moment, there are a lot of interrupted time series looking at the impact of COVID, for example. Here's a study looking at the impact of the economic recession. So these are things which are impossible to randomize because they happen without us necessarily knowing that they're even going to happen, but we can use data from the past to have a look at what's happening in the present and make some inferences. Today, we're going to work through an example. This one is an interrupted time series that looked at the long-term effect of reduced pack size of paracetamol on poisoning deaths. This study has many outcomes. We're just going to look at one today and follow through some of the process. I find it useful to sort of use a PICO framework. Obviously, we can't use it in the same way we would for other studies, but it's useful just to get our head around what's happening. So here, our population was England and Wales. The intervention being looked at was UK legislation, September 1998, that restricted pack sizes of paracetamol. Now, our comparison here, rather than comparing two different groups at the same time, we're actually comparing a group before the intervention took place and after the intervention took place at a population level. And of the various outcomes in this particular study, we're going to look at mortality. So that's kind of our framework for the study. We're going to move on now and actually look at the data from that study. And here we've got data collected from a group of individuals, in this case, the population of England and Wales. Our y-axis here is the number of deaths. And we can see here we're looking at time on our x-axis here from 1993 all the way to 2009. In addition, when we're conducting interrupted time series, we usually aggregate data at different time points. Here, they aggregated quarterly. It's very common to aggregate monthly as well, or yearly. The reason this is important to note is because it comes into how we frame the definitions of our outcomes. And Lizzie will talk a little bit later when we come to meta-analyze. What do we do if we've got some studies that aggregate at different levels? So we might have some studies at quarterly, some at yearly. We've got a nice clear intervention time. They estimate the first impact just after the intervention took place in 1998 in the fourth quarter. And what that does is neatly divide our time series into two segments. And that's why they're called interrupted time series. We have a time series that's been interrupted. Now, I'm quite a visual learner and I love graphs. And Joe kind of hooked me onto interrupted time series because they're so nice to look at. You can see the data and have a look at the trends, and it's very clear. It's very simple to pop in your research so that anyone can understand what's going on. One of the key strengths of an interrupted time series is that it takes into account any trends in the different segments. So we could just do a simple before and after and measure the average number of deaths before and the average number of deaths afterwards, but that's not giving us all of the information. Here we can see in our post-interruption trend, it's definitely heading downwards. And if we just did a before after, we would miss that entirely. The way that we compare our two groups is by looking then at what might have happened if there had been no interruption. So we create this counterfactual by modeling the trend in the pre-interruption and predicting that forward through time. And the suggestion there is that if there had been no interruption, the data would have continued on this trend. And now what we've got is a way to compare what we do actually see in the data with what we would have expected to see if there had been no interruption. Now, there are many different ways that we can measure the difference. Today, we're going to focus on the main ones that are used. First off is our immediate level change. And that's measured by this orange arrow here, the difference between the counterfactual and our post-interruption trend right at the point of the interruption. Now, you can imagine for some interruptions, this might come as a big immediate change, and for others, it might not. And for those where it might not happen immediately, we might expect to see some change in trend. And so another way to measure the impact is to look at the change in slope between what we expected was going to continue happening and what we actually see. Another quite common measure of impact is to look at the level change long term. So down the track, after maybe we've had some time for the intervention to take hold, we can look later and see a long-term level change. Now, these are three common ways to measure the impact. There are others as well, but these are the most common ones. So moving on to how we can actually get numbers to go with those colorful arrows. Today, I'm going to walk you through the most common type of model that we use, and it's called segmented linear regression. There's some nice parameter formulas here that on the face of it look quite complicated, but I'm going to step you through them one at a time, and you'll see that actually they're fairly straightforward. Plus, the computer does most of the work for you anyway. So here we start off with a beta naught, and that's just our y-intercept. And you can see here that when the data started on the very beginning of that trend, our number of deaths was about 31.6 per quarter. It was trending slightly upwards, and our beta 1 parameter multiplied by the time since we started measuring tells us the slope in this pre-interruption phase. And here we can see it's 0.09, very slightly upwards. Now we get on to the interesting ones. Our beta 2 here is our level change. And here we can see an immediate level change of -6, so 6 fewer deaths per quarter at the time of the interruption. And the way we model that on the computer and with our data is we have this IT, and that's just an indicator variable. And on our spreadsheet with our data, that's just zeros before the interruption and 1 after the interruption. So it's acting like a switch at the time of the interruption. Finally, the most complicated one here is our beta 3, which is measuring our change in slope from the counterfactual to our post. And the reason we've got these extra t's in here is because we're creating a new time variable that is 0 before the interruption. And then after the interruption, we just increment upwards, 0, 1, 2, 3, on and on and on. And then again, we've multiplied that by our I, just to make sure it's 0 before the interruption. So that gives us our slope change. And we can see here it's -0.36. So every quarter, there's 0.36 fewer deaths. Now, sometimes we want to know the value of the actual slope. The beta 3 there tells us the change in slope. But if we want to know the actual value of the slope, that's very simple to calculate. It's simply the sum of our slope beforehand and our change. And so in this case, it's about -0.27. Finally, as with all of our regression models, we have this error term right at the end of our model there. And that's just to account for deviations from our model. We can see that the data points don't all exactly line up on our trend there. There is a little bit of scatter. Now we're going to talk a little bit more about those error terms and how they can make for some complexity in just a little bit. But first, we thought it might be useful to walk through again these common impact effects and how we might describe them in words. So our first one is our immediate level change. And that's simply, in this case, the absolute decrease in the number of paracetamol-related deaths when the interruption first occurred compared to if that interruption had not occurred. Our slope change is, in this case, our decrease in the number of deaths that occur per quarter compared with the pre-interruption trend. And finally, our long-term level change has a slightly more complicated looking formula, but all we're doing here is we're taking our level change and then we're adding our slope times however far down track we're interested in looking. So in this example here, if the time of interest was the fourth quarter of 2005, 7 years after the interruption, we would see that our long-term level change is -16, which is quite considerable. If you recall that the very beginning of the time series, there were about 30 deaths per quarter. So we're looking at quite a substantial decrease there. So these are the most common ways to measure the impact. All through both Lizzie and my presentation, you'll see down the bottom some references. These slides will be made available. So if you're keen to look up some more of these sorts of information, then please feel free to use those references. Now, complexities, why you might need to consult a statistician. I know sometimes that's difficult, but these can be quite tricky sometimes. For starters, our time series data are not always independent. Now, what do I mean by that? Well, in the model that we fixed here, this error term turns out to be quite important. Now, these two pictures here are just some data that I've simulated that use exactly the same numbers for all of our betas, but I've done something slightly different with the error term from one to the next. In the first one, our error term is just normally distributed data. It's just very random. You can see that the little gray data points are just randomly scattered up and down as we go along the trend lines. But we can see a difference in the second graph here. We can see there's some patterns that are here in our data. Now, those patterns are caused by autocorrelation. Now, all that means is that our error terms are no longer totally independently random. They're somewhat influenced by previous data. Now, autocorrelation is very frequent in time series data. One of the more common types of autocorrelation we see is seasonal autocorrelation or seasonality. Here again, these two graphs use the same numbers for all the betas, but in one of them, I've added a 12-monthly seasonality term, and you can see it going up and down. And you can imagine this happens with many types of illness, where people might tend to get sicker in winter than in summer, and other things as well. Now, one of the reasons why this is very important to take into account is that if you don't take it into account, then what you get are artificially small standard errors, which makes your confidence intervals narrower than they should be. In addition, with seasonality, the actual timing of the interruption as it approaches a peak or a trough, depending on where they line up, that can also introduce bias into your results. So it's very important to take these into account. Now, one of the reasons this is complex is because these make the modeling more complicated, but also we need a reasonable number of data points in order to actually estimate and adjust for these. So 12 to 24 data points, usually for sort of lag 1 autocorrelation, which is when the autocorrelation depends on the point for it. In seasonality, you need several cycles of seasonality in order to work out exactly what's happening there and adjust for it. Now, in some types of studies, that will not be a problem. They will have plenty of data, but often with public health studies, we found that we don't often have lots of data points. And again, Lizzie's going to show some examples of this later and how that can impact how we might want to meta-analyze multiple interrupted time series studies. The type of data that you've got, whether continuous data or count data, these all require different statistical methods as well. So you may need to be consulting a statistician for some of these complexities. Something I also glossed over just because I picked an easy example to work through as our worked example, is that the interruption, it might not be just as straightforward as before and after there being a nice, straight, clean jump. Here are some examples from some excellent research papers that show multitude of different ways that we could model the impact. You can see some of these, there is no level change. Some of them, the level change comes a bit later than the intervention. There's all sorts of different ways this can happen. And this will require not just statistical support, but we also need people who actually know what the data should be looking like and how they might expect things to go. So some clinical expertise as well. We could also have multiple interruptions. So there's lots that can happen here. And finally, in terms of complexities that we're going to talk about today, sometimes we have control series. Now, these are important because we assumed that the change that we saw in our data in our example was from the change in the paracetamol packet size laws. Now, if you had a control series in a different country or somewhere where you would expect what you're looking at to have no impact, then that can strengthen your opinion on whether this impact is legitimately from that interruption or not. So in these two examples below, we've got two data series, a red one and a blue one. And in the first one, we can see at the time of the interruption, the red one changes and the blue one doesn't. Now that would be a stronger suggestion that our intervention did impact one without the other. In the next one, however, we see that at the time of the interruption, both the red line and the blue line change. Now that's indicating that actually the interruption has affected something that we might not have expected it to, and therefore there might be some other intervention at play that we might not have taken into account. So these are very, very complex when we have lots of data like this. Now, why might you care about this as a systematic reviewer? Well, we know that methods and results are often incompletely reported, and sometimes we have to go back to authors to get some more data. We might have to work out how to get a standard deviation that hasn't been reported. Because we have multiple different ways of measuring impact in an interrupted time series, this can add another layer of complexity. For example, you might have one study that has just reported the before and after, which, as we said before, isn't taking into account trends. We might have one study that is reporting a level change and a slope change, and then we have to decide which measure of impact are we more interested in, level changes or slope changes, or do we need to do two separate analyses? Another study might report the level change at a later time. And then, of course, you may have some studies that have accounted for some of these complexities and others which have not. And we might want to make sure that all of the data that we have is analyzed in the same way. How often is it likely? Lizzie's review that she finished just a couple of years ago, she looked at systematic reviews that incorporated interrupted time series and found that 68% of them did reanalyze the study data, so quite common. Now there's good news though. I feel like I've been telling you bad news for a while. It's quite easy to actually obtain interrupted time series data. Unlike other study designs, you don't necessarily have to get the individual participant data. As well as that, if you can't access the data from the study itself or from the authors, most interrupted time studies include a graph, like the ones that we've been showing here. And nowadays, it's very straightforward to use digital data extraction to actually obtain data from the graphs. We did some work on this and just published last year where we had a whole lot of graphs from papers that we also managed to obtain the original data. We then extracted the graphs using digital data extraction to compare accuracy and found that actually it's very accurate. If you're interested in this, the link that's here on the page will take you to both the paper, and we made sure that we put a video tutorial on there as well to make it as easy as possible for people to be incorporating interrupted time series in their systematic reviews. There are more and more interrupted time series studies coming out. I suspect even more so after big global events like economic crises and COVID. So that's feels like a very brief overview of interrupted time series analysis. I think we've got a couple of minutes for questions before I hand over to Lizzie to talk about meta-analyses. So if you've got some questions, that would be great. I'm happy to answer them now, or if you don't think of them till later, if we've got time at the end too.
Great. Thanks so much, Simon. We have a question from Ernest in Greece, and the question is really around the duration of the intervention. So they're asking whether the intervention has to be short, briefly executed, or the interruption line depicts the point onward from where the intervention occurs.
Yeah, that's a super great question. And that comes back to to these sorts of graphs here, where the example I showed was really one where there was a short, sharp interruption. And so it was a nice clean split into a pre-section and a post-section. Now in real life, that doesn't always happen. And it doesn't need to either. It makes for a simple example, but you can do an interrupted time series with, for example, this graph over here shows a line coming in a pre and then kind of a grayed out period and then a line post. And those you will often see where people have got some sort of roll-in period or they've allowed for some sort of time over which that interruption or intervention is taking place. So some hospital work, for example, where they're rolling into a new system of doing things, they have to allow some time for that to all settle before they want to compare how things were with how things are. And so in that case, there's several different options you can use for that. So it doesn't have to occur in and at one exact moment. It's just easier if it does. Real life is often more messy, but that's okay. And again, this would be something where it would be useful to have a check with a friendly statistician. And some of these papers that I've linked here also have advice on what to do when your intervention is not happening just nice and neatly at a single sort of point in time. So hopefully that has answered that question.
Yes, hopefully. I think that does. We haven't got any other questions at the moment. Maybe just a question for you around if you could briefly describe some of the kind of methods that are used to adjust for seasonality and how they might differ depending on the length of series.
Sure. So when we've got seasonality is difficult to work with if you don't have lots of data. If you've got plenty of data, then you can model, actually according to the time periods that you've got here. So if you're expecting, for example, yearly data and you've got monthly data points, then you can model those sort of sine waves there, and that helps account for the seasonality. In terms of autocorrelation, there are a few statistical methods. Matter of fact, at the bottom of this slide, we looked at both with simulation studies and empirical studies, quite a few different statistical methods out there to account for autocorrelation. Restricted maximum likelihood is one method. Price-Winston is another statistical method, but most of these will account for the autocorrelation and automatically adjust so that your standard errors and confidence intervals are back where they should be. Whereas if you do use just an ordinary least squared, they'll be too short. But as I pointed out here, you do need a reasonable number of points in order to make those assumptions and make those modifications.